This is the first time something like that is observed, where there is a glow ahead of the object towards the sun. And now, as it approached closer to the sun, there seemed to be some
fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth.
A swirl of excitement rippled through the astronomical community when Avi Loeb unveiled what he described as the best image so far of 3I Atlas, asserting that the object is not behaving like a conventional comet. What made his revelation so dramatic is that it came dressed in provocative implications. This interstellar visitor may not be a comet at all, but something far stranger. The image in question, taken by the Hubble Space Telescope on July 21, 2025, shows what appears to be a glowing envelope of light ahead of the object's solar-facing side, with little or no evidence of a classic cometary tail trailing behind. Loeb argues that this glow is incompatible with the expectations for dust swept back by solar radiation, and he suggests that the nucleus itself may be dominating the light, raising the tantalizing possibility that 3I Atlas is generating or reflecting light in a manner unlike any comet we've known. Before we start, smash the like and subscribe buttons for more updates. From the moment the image circulated, it provoked fierce debate. According to Loeb, the absence of a discernible tail is not a trivial omission. For a body heated by the sun and shedding dust, one would expect the dust and small particles to be pushed outward into a tail that extends away from the sun, visible in high-resolution images. Yet here, the elongation seems to lie sunward, not anti-solar. This peculiarity underpins his argument that the object may not be shedding dust the way a normal comet would. If dust particles of typical micron-scale size were being released, solar radiation pressure would push them into a visible tail. The fact that telescopes did not capture such a tail suggests, in Loeb's view, that the dynamics of light and particle ejection in this case do not follow conventional cometary behavior. Loeb has pressed further. The brightness profile in the Hubble image, he contends, is so steep that the nucleus must contribute a dominant portion of the observed light. Under that reading, the coma's glow is not traveling outward symmetrically but concentrated close to the core, with minimal extension. He reasons that if the nucleus itself is luminous, either by reflecting unusually brightly or by emitting light, it would greatly reduce the need for a dust-laden coma to explain the observed signal. That in turn lowers the amount of dust or gas that must be present and calls into question how much sublimation is actually happening. If the cometary hypothesis were correct, a more extended tail of dust and gas would likely be visible, especially given the imaging capabilities now focused on the object. One of the more startling possibilities Loeb raises is that the object might have an active, perhaps artificial component, that it could be a spacecraft, a probe, or a body powered by processes not typical of comets. He frames this not as a definitive claim, but as an alternative worthy of attention. If 3I Atlas is emitting or reflecting light from its nucleus, the implied size of the object would be smaller than initially estimated, possibly shifting the scale down from kilometers to tens or hundreds of meters. Lower size would make it less obviously massive and more compatible with behaviors that deviate from what we expect from large icy bodies. Under that scenario, what we see as a coma might be dust scraped or blown from a surface, not sublimated from deep ices, and the light signature could include emissions or reflections, unlike purely solar scattered light. But these claims hinge on a delicate balance of observational detail and interpretation. The Hubble image does show a fuzzy glow surrounding 3I Atlas, but its lack of a prominent tail is a non-conclusive clue. Some of the fuzziness could arise from image smearing due to the object's motion during long exposures, or overlap of background stars. The stacked images used in many observations aggregate many frames and can introduce artifacts. In fact, when early reports first flagged this object, the Minor Planet Center classified it as a comet based on hints of fuzzy light and possible extension in the imagery. That tentative classification echoes the uncertainty inherent in distinguishing a faint, fast-moving interstellar object amid the vast star fields. Further complicating the picture, some of Loeb's arguments rest on the premise that any dust ejected would remain small enough to be pushed outward. But if the dust is much larger, or charged, or subject to non-standard forces, for example, electromagnetic interactions, its behavior might depart from the simple model of solar radiation pressure-driven tails. Loeb himself has explored how particles might acquire charge in the solar wind or in the ambient medium and interact with electromagnetic fields, influencing their trajectories in surprising ways. He and collaborators have attempted to model mass loss rates, drawing on estimates of how far the coma glow extends before being halted by ambient pressure, and to map how dust density might attenuate with distance. That modeling suggests a mass loss rate of about 10 kilograms per second under certain assumptions, which is modest for a comet but not negligible. At the same time, new spectroscopic data from the James Webb Space Telescope complicates the clean separation between natural comet and exotic anomaly. JWST observations revealed a coma dominated by carbon dioxide, with water and other volatiles present in smaller proportions. The CO2 to H2O ratio is unusually high compared to typical comets, exceeding trends observed among known long-period or Jupiter family comets. That suggests either that 3I Atlas formed under different chemical conditions, or that some processes are suppressing water sublimation. The presence of water and dust still supports a comet-like model. Yet the dominance of CO2 raises questions about the uniformity of comet chemistry across different star systems. Loeb views that CO2 dominance as another clue. If the nucleus is unusually rich in CO2, or has physical layering that favors CO2 release over water, that might reduce the expected dust outflow or tail formation, making the object appear anomalously quiet. In his view, the disparity between predicted tail strength and observed lack thereof strengthens the case for a nucleus-centered light emission. However, most comet specialists interpret the high CO2 content as indicative of compositional diversity rather than evidence of artificial origin, an exotic but still natural object. In their interpretation, 3I Atlas may simply be an interstellar comet whose physical and chemical properties are unlike solar system comets because it came from a different environment. Even more intriguing is a phenomenon that Loeb and his collaborator Eric Kito have explored: the presence of an anti-tail, an elongation of the coma in the direction of the sun rather than away from it. In their recent physics modeling, they propose that this sunward extension arises from anisotropic sublimation. Because the sunlit surface ejects particles with higher flux and perhaps larger grains that can survive longer near the sun, the effective snowline or survival radius of sublimating grains becomes skewed. The anti-tail might then represent a directional extension of particles that survive longer in the solar-facing hemisphere. That kind of extension is not a classic tail, but is nonetheless a directional feature whose presence raises questions about the symmetry one expects from cometary outflow. If the anti-tail is incorrectly interpreted as a sign of anomalous behavior, it could be misread as a sign of artificial emission rather than natural sublimation geometry. The implications of Loeb's unveiling and his interpretation are profound if one allows the possibility that 3I Atlas is not a typical comet. If this object is indeed a probe or artifact of some extraterrestrial origin, it would be the first object of its kind ever accurately imaged on a trajectory passing through our solar system. It would challenge many assumptions about what interstellar visitors might look like, how they might behave, and how we should design observational strategies to detect them. It could open a new frontier in which interstellar objects become potential targets of techno-signature searches. The very fact that Loeb is willing to entertain and promote this possibility forces the broader scientific community to examine the boundaries of interpretive caution. Even if 3I Atlas were ultimately confirmed to be a comet, Loeb's image and interpretation serve as a powerful test case. It demands that astronomers refine models of dust ejection, sublimation asymmetry, electromagnetic interactions, and the limits of imaging sensitivity. It reminds us that we have so few examples in the interstellar realm that any anomalous visitor must be scrutinized from multiple angles. In this sense, his revelation may catalyze methodological advances, making future detection and classification of interstellar bodies more rigorous. If, however, Loeb is right, or partially right, the consequences are nothing less than paradigm shifting. The notion that an object traversing interstellar space might harbor active nucleus-level processes not accounted for in comet models would force us to rewrite parts of astrophysical theory. It might suggest that probes or artifacts could journey between star systems, and that interstellar archaeology might be within reach. That in turn would force rethinkings in planetary defense, surveillance, and telescopic targeting. Scientific standards for object classification would need to expand to accommodate borderline or hybrid objects, those between natural and artificial. Moreover, the stakes are not just academic. Public interest in the possibility of alien probes is enormous, and Loeb's reputation as a provocateur in the search for extraterrestrial technosignatures gives the narrative extra weight. If leading observatories or missions begin chasing objects with that mindset, funding priorities and instrument design might shift. Observing campaigns might need to prioritize signatures of light emission, unusual brightness profiles, or trajectory fine-tuning, in addition to conventional cometary activity. Yet the danger of hasty conclusions is real. If the scientific community rushes to claim discovery of an alien probe prematurely, it risks public embarrassment, reputational damage, and mistrust. The rigorous path demands that each anomalous feature be tested, modeled, and confronted with alternative explanations. That means accumulating data across the electromagnetic spectrum, capturing high-resolution spectra, polarimetry, infrared imaging, and even coordinating spacecraft observations when feasible. Loeb's image and his claim that 3I Atlas is not a comet forced that agenda into public view. Looking ahead, the upcoming perihelion passage of 3Y Atlas, its closest approach to the Sun on October 29, 2025, stands as a crucial test. If the object begins to exhibit strong enhanced outgassing, a dramatic increase in dust tail formation, or other classical cometary signatures, that would tilt the balance toward a comet interpretation. But if such activity remains muted or asymmetric in unexpected ways, Loeb's interpretation will gain momentum. The timing, geometry, and consistency of brightness changes will become critical pieces in the puzzle. Loeb himself has flagged that observable event as a litmus test. If 3I Atlas erupts into full cometary behavior, that would reinforce a natural origin. But failure to do so or continued anomalies would deepen the mystique. In the meantime, telescopes around the world are prioritizing follow-up, spectroscopy, and polarimetry to capture subtleties in the light signature and polarization behavior, data that may discriminate between a dusty coma and nucleus-centered illumination. The very image that Loeb released has already galvanized deeper scrutiny of how subtle features and brightness gradients can carry outsized interpretive weight. Resting on a single revealing snapshot, his claim forces a richer dialogue about what interstellar objects can be, and what we should cautiously expect to see. In sum, the unveiling of this image by Loeb, tied with his bold assertion that 3I Atlas is not a comet, marks a turning point in the study of interstellar visitors. Whether that claim holds or crumbles under further observational weight, it has already reshaped the framing of future detection, encouraged a willingness to entertain hypotheses beyond the conventional, and challenged astronomers to sharpen both instruments and imagination. The cosmos may be more mysterious than we had assumed, and as Loeb's revelation underscores, sometimes the anomalies are the most instructive windows into what we have yet to learn. The glow ahead of 3I Atlas in the Hubble image stirs deep unease in conventional thinking. Rather than trailing dust and gas in the classic wake of a comet, this object seems to carry its light forward, as though its head is lighting the way. If one accepts that the image convincingly shows a sunward-facing luminous envelope, then the question becomes, what physical process can support such a structure? Loeb presses this question without flinching. Standard sublimation-driven comas struggle to produce that kind of directional glow, especially without a matching tail. The core brightness profile suggests the central region outshines the outer cloud, which invites speculation about intrinsic light generation or highly reflective surface phenomena. Loeb's view hinges on the possibility that radiation from the nucleus itself plays a role in what is observed. If the nucleus reflects light more brightly than typical comet nuclei, or if it engages in some form of active emission, then the observed glow need not be entirely the result of dust-scattering sunlight. In that scenario, the cometary model must be supplemented with additional processes. Recognizing the boldness of that stance, Loeb frames it not as certain, but as a hypothesis worthy of rigorous testing. He invites the broader community to consider hybrid models, neither pure spacecraft nor pure icy body, but something in between. He also explores the dynamical consequences of such a hypothesis. A more luminous nucleus would reduce the required fraction of dust or gas needed to explain measured brightness. That in turn softens constraints on mass loss rates and dust production, permitting interpretations that depart from classical comet models. This line of reasoning helps him argue that the amount of dust inferred under normal assumptions might have been overestimated. If the dust component is lower, then one would naturally expect a weaker tail. That leads to a tension. If the tail is absent or weak, it may not require rejecting the cometary origin outright, only modifying the assumptions about mass loss and scattering efficiencies. At a deeper level, Loeb probes the trajectory of 3I Atlas. He notes that its orbit lies very nearly in the ecliptic plane of the solar system, within a few degrees, which seems surprising for a random interstellar arrival. He calculates the odds of that alignment and finds them low, on the order of 1 in several hundred. For a purely chance object to slip so neatly into the planetary plane seems coincidental. He also points out that the orbit is retrograde, moving opposite to the direction of the planet's orbits, which adds to the anomaly. These orbital features, he argues, invite curiosity. Is the path natural or engineered? Loeb and collaborators have modeled possible non-gravitational accelerations for 3I Atlas. Typically, comets deviate from purely gravitational trajectories due to jetting of gas and dust. But for this object, the deviations appear larger than one might expect from a modest comet, and the direction of those accelerations may not match standard outgassing models. If the non-gravitational forces are unusually strong or anomalously directed, then one must consider that forces other than gas jets may be at work. Perhaps photon pressure, electromagnetic interactions, or even engineered propulsion. While the data remain ambiguous, those deviations provide a critical test. If they scale with distance or solar flux differently than sublimation-based models predict, it would strengthen the case for something more exotic. Loeb also delves into statistical population arguments. He questions whether there exist enough icy bodies in interstellar space to account for a large interstellar comet like 3I Atlas casually passing through the inner solar system. He suggests that the inferred number density of interstellar comets with enough cross-sectional area to be detected is already strained. If one assumes natural origin, one must accept that we happen to observe a rare, large object. He counters that the only way to explain its brightness, lack of tail, orbital alignment, and non-gravitational forces in one package is to entertain the possibility of an artificial component. To flesh out these ideas, he and his team produced toy models blending reflectivity, emission, and dust. In such models, a compact object with a reflective or emissive surface combined with a modest layer of dust could mimic many of the observational signatures. That hybrid model softens the leap from not a comet to alien probe. It allows for a continuum of possibilities. Perhaps it is a relic or artifact that has been coated by dust, or perhaps a natural object with unusual surface or internal composition. The boundary between natural and artificial becomes blurrier. Loeb also engages with counterarguments. He addresses the possibility that the observed elongation of 3I Atlas in images might arise purely from motion blur. Given its high speed tens of kilometers per second relative to long exposure times, the object could smear slightly. He notes, however, that if the elongation fits precisely what one would expect from motion blur, then the apparent tail may not be intrinsic at all but an artifact of imaging. That means some reported tail features, especially those only marginally above noise, might warrant re-examination under more stringent image processing. He emphasizes that resolving the full point spread function of the instrument, correcting for motion, and stacking frames in different ways becomes essential. Another nuance he raises is the possibility that dust particles are larger or more complex than often assumed. Micron-sized dust is easily influenced by radiation pressure, but centimeter-scale grains or electrically charged grains may resist that push, linger near the nucleus, or follow more complex trajectories. If the dust is clumpy or irregular, or if it carries significant charge, then interactions with solar wind magnetic fields could further warp expected motion. In extreme cases, charged grains might even spiral or shuffle around the nucleus, smearing out a classical tail structure. So the absence of a tail doesn't necessarily imply absence of dust. It may just reflect complex physical behaviors. He also considers sublimation anisotropy. The illumination and heating across the surface may not be uniform, leading to directional ejection of gas and dust. If the sunward side is more active, that could produce a plume that bulges forward before dust is carried away. Loeb posits that the sunward glow may therefore represent a forward leakage rather than a tail in reverse. That shifts the paradigm. Instead of a classic tail pointing away from the sun, one might see a forward plume if sublimation is sufficiently intense and asymmetric. Loeb's predictions include testable ones. If the object remains anomalous through perihelion, its closest approach to the sun with suppressed classical signatures, then his model gains traction. If dust tail growth lags behind expectation or appears oriented wrongly, that would also support the hybrid hypothesis. On the other hand, if water lines, dust expansion, or sudden outbursts occur in expected patterns, that would tilt the balance back toward a cometary origin. He also draws analogies to the earlier interstellar visitor Oumuamua, which remains controversial. In that case, anomalous non-gravitational acceleration, lack of cometary signature, and odd shape invited speculation about a thin sheet or solar sail. Loeb sees 3I Atlas as a more promising candidate for rigorous testing because it is brighter, has an observable coma, and will move closer to the sun. Where Oumuamua hovered in ambiguity, 3I Atlas might force a decision. Assessing impact, Loeb suggests that if even a fraction of interstellar visitors harbor technological signatures, then our approach to astronomy and exploration must shift. We will need detection pipelines that flag brightness profiles, alignment anomalies, and trajectory oddities in real time. Observing proposals would need to prioritize multi-band follow-ups, polarimetry, spectroscopy, and non-gravitational acceleration measurements for every candidate. Furthermore, he contends that classifying interstellar visitors purely by analogy to solar system comets may blind us to novel kinds of objects. Instead of assuming comet by default, the classification framework should allow for gradients from pure ice to hybrid to engineered. In that sense, his unveiling forces a reevaluation of taxonomy. Perhaps interstellar small bodies should be the default category until internal composition and behavior are fully constrained. Matter and motion debates swirl. If 3I Atlas is partly artificial, how might it have survived interstellar travel? What materials and shielding might preserve an emissive surface coated with dust over eons? Loeb speculates that if the object is old, it might be dormant for most of its journey, reactivating only when exposed to solar flux. Dust layers might protect pristine surfaces. In that sense, its behavior would resemble a sleeper probe, only revealing anomalies under energetic influence. Loeb also wrestles with the notion of directionality. If the object were directed intentionally toward our solar system, how precise must the aim be? Given the vastness of interstellar space and the motion of stars, targeting the ecliptic plane is non-trivial. He speculates that if the path is optimized, then the chance alignment of the orbital plane within a few degrees is less random than assumed. That raises deeper questions. Is it plausible for a civilization to send probes directed into planetary ecliptic planes? Could intelligent actors foresee where planets mostly orbit and bias their trajectories accordingly? If so, then the geometry of 3I Atlas's orbit may be interpreted as a clue rather than coincidence. The challenge of energy and propulsion looms. If 3I Atlas is a probe, what drives it? Loeb allows that photon pressure light sail dynamics, electrostatic interaction, or even internal microthrusters may be possibilities. If photon pressure were significant, it might contribute a small acceleration proportionate to distance from the sun. In that scenario, the non-gravitational acceleration might scale differently than in sublimation models. That offers a diagnostic. Compare acceleration versus solar flux curves to see whether the force scales like 1r2 as photon pressure would, or with sublimation-driven gas momentum, which might scale more steeply or irregularly. Loeb also considers polarization signatures. If the nucleus or dust is coated or structured in certain ways, polarized light reflecting off surfaces could betray unusual geometries or materials. He argues that polarimetry may distinguish between scattering from dusty comas and specular or semi-specular reflection from smoother surfaces. A polarized brightness signature that deviates from comet norms could hint at something engineered or unusual. Another consideration is temporal variability. Comets sometimes jump into more active states via outbursts when subsurface material is exposed. Loeb argues that if 3I Atlas were acting like a comet, we might expect sudden jumps or changes in coma brightness or tail structure. If such variability is absent, or if changes follow different patterns, then that is a clue. He proposes careful, continuous monitoring to capture light curves and morphology changes. Loeb issues a warning about cognitive bias. Scientists may dismiss anomalies too quickly or shoehorn data into conventional models. He argues that openness to anomalies is scientifically healthy, so long as extraordinary claims are balanced by rigorous evidence. He wants the community to remain skeptical, but not closed. The revelatory image he presented is a provocation. It demands that radically different hypotheses be tested rather than dismissed out of hand. Yet Loeb knows the stakes. If 3I Atlas cannot be shown convincingly to depart from comet behavior, his hypothesis will likely fade. But if it does show unexplainable deviations, it could reshape the search for techno-signatures. He sees this as a low-cost probing of the universe. We already have telescopes and survey systems. We need only to train our filters to notice anomalies and act on them. He also contemplates policy and response, assuming his hypothesis holds weight. He imagines an international Turing test of sorts, humanity's reaction to an interstellar object that might be technological. He raises questions of whether we should broadcast, intercept, or study passively. Though beyond observational science, these considerations underscore that discovering a potentially artificial interstellar object would not be purely academic. It would carry existential, diplomatic, and strategic dimensions. Loeb's revelation thus stretches wide across observational astrophysics, planetary science, and even the philosophy of science. If 3I Atlas turns out to contain hints of technological origin, that would spark not only a scientific revolution, but a societal one. We would have, in effect, tangible contact with something beyond Earth without missiles or radio signals, just a visitor in our instruments. The protocols for how to interpret, announce, and engage with such a discovery would need to be rapidly refined. At its core, the event of Loeb revealing that image and refusing to accept the comet classification uncritically underscores a shift in how we might approach interstellar visitors. No longer will faint fuzziness and spectral lines be sufficient. Minute brightness gradients, motion-corrected imagery, polarization signatures, and trajectory oddities will all gain heightened weight. The boundary between what is considered plausible science fiction and what is observational astronomy becomes thinner. To those who argue that natural explanations are overwhelmingly more likely, Loeb offers a counter, that science advances through confronting the unlikely. Just as past anomalies led to paradigm changes such as the discovery of pulsars or quasars, perhaps 3I Atlas could be the crack in our preconceptions. In that light, his controversial presentation of the image is not a stunt, but a strategic jab. It forces the community to sharpen its tools, question its priors, and open pathways to new possibility. Whatever the outcome, the memory of that image, as labeled not a comet by one of the most provocative voices in the field, will be etched in the record of interstellar astronomy. It will become a reference point. The moment when conventional wisdom was challenged not by some abstract theory, but by a resolved snapshot of a visitor whose behavior evaded simple categorization. In studying it, we may either reaffirm our frameworks or take a first step into a more audacious view of interstellar reality. Loeb's assertion about 3I Atlas not being a comet also nudges attention toward how future detection pipelines should adapt. In particular, survey telescopes could embed anomaly detectors that flag objects whose brightness decline or spatial morphology deviates from standard comet models. For example, if an interstellar object shows a brightness falloff steeper than typical comet Comet or an unexpectedly compact coma, automated systems could flag it for rapid follow-up. That kind of algorithmic triage would allow us to catch the next weird visitor early, rather than discovering anomalies only after months of routine observation. Another dimension Loeb introduces is comparative analysis among multiple interstellar candidates. If more interstellar visitors are found, analysts could plot them along axes such as coma-to-nucleus flux ratio, non-gravitational acceleration strength, tail length versus heliocentric distance, and orbital inclination relative to the ecliptic. In that parameter space, 3I Atlas might lie far from the cluster of ordinary comets if any such cluster exists. That departure would serve as a benchmark. Future objects might align more with classical comets or stray into the anomalous regime. In that sense, 3I Atlas becomes a kind of reference prototype for odd interstellar object classification. Loeb also emphasizes the necessity of multi-wavelength coordination in real time. Visible light imaging is powerful, but far more discriminating power comes if one can combine ultraviolet, infrared, submillimeter, radio, and X-ray observations. If 3I Atlas were emitting remotely detectable features beyond reflected sunlight, say thermal anomalies, non-thermal emission lines, or localized heating signatures, then we might see discrepancies between thermal infrared expectations and simple solar illumination models. For instance, if the infrared signature indicates a higher temperature than passive solar heating would predict, that could hint at endogenous energy sources. Coordinated observation across disparate instruments and wavelengths becomes essential in testing Loeb's hypothesis. He also argues for precise astrometry improvements. If the object's position deviates at minute levels from predicted orbital paths, that could betray subtle, continuous accelerations. Even millisecond errors in position, when integrated over days or weeks, may reveal force vectors inconsistent with pure gravitational plus sublimation models. In practice, that means observatories might need to push the limits of astrometric precision, revisiting archival frames and reprocessing images with more refined calibrations. The image Loeb released, then, serves less as a conclusion than as stimulus, a clarion call to sharpen instrument calibration, photometric reduction pipelines, and motion correction techniques for rapidly moving bodies. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Avi Loeb's 3I Atlas image? Do you think it's not a comet? We want to hear from you. Thank you for watching and see you next time.